Let's define Riemann sum for the topic of definite integral. So what is a Riemann sum? Now the definite integral is said to be originated from Riemann sum, dedicated to the famous mathematician Riemann. So coming to Riemann sum, initially I assume a function f from the closed interval AB to set of all real numbers. Now f from closed interval AB to set of real numbers be a bounded function. Now what do we mean by bounded function is the biggest question in this sentence. When I say bounded function, that means the function has limited real number on the left and on the right. Mathematically, we define, that is, there exists m belonging to R such that mod f of x is less than or equal to m, is how we mathematically define the boundedness of a function using the real number m. So therefore, I assume that f from AB to R is a bounded function. And for this, I also assume that P is equal to the first value being x0 assumed for A, and next being x1, x2, x3, xi minus 1, xi, and xi plus 1, and xn minus 1 and xn is what we call as partition. We have already defined for this B the partition of the closed interval AB. And let me take some interval Ti is closed interval xi minus 1 and xi. So I assume the interval Ti as xi minus 1 and xi, for which I am going to define the Riemann sum. So with the assumptions of f being a bounded function and P the partition of AB and the interval this, we know that the length of the interval delta Ti is nothing but xi minus xi minus 1, or this is how we define the delta Ti. Now, assuming on this, we define the Riemann sum denoted by SPF. The Riemann sum denoted by SPF is defined as summation I running from 1 to n of f of Ti delta Ti, f of Ti delta Ti is what we get when we assume this. So the Riemann sum is generally denoted by SPF and is defined as sigma running from I equal to 1 to n f of Ti delta Ti, where f of Ti is the function as defined with the closed interval AB to the set of real numbers, and delta Ti is the length of the interval xi minus 1 or xi, or you can also define this with delta xi, but both are the same, denoted by this. Now let's define the definite integral using the Riemann sum. So now we know that the Riemann sum denoted by this for the partition P and the bounded function f is defined as sigma I running from 1 to n f of Ti and delta Ti. So using this definition of the Riemann sum, the lower integral, the definite integral is defined as integral a to b using the bounds for the function, because the function f is bounded, and f of x dx, where a is called the lower limit and b is called the upper limit. So using the boundedness of the function, we have the lower limit which is a and the upper limit which is b, and hence the definite integral using the Riemann sum SPF equals summation I equals 1 to n f of ti delta I is defined as integral a to b f of x dx. Also, as I see this integral, we see that the bounded function f of x as seen in this integral is called the integrand. The bounded function f of x is referred as integrand of the definite integral this. Therefore, the Riemann integral of the function f of x is defined using this as limit norm p tending to 0 of SPF with the partition norm tending to 0 of this, and therefore we substitute this and into the function. That is, this reduces to limit norm p tending to 0 of SPF, which is summation I running from 1 to n of f of ti of delta xi, which is xi minus 1, which we have because the interval ti is xi minus 1 and xi. So using this interval, I have my Riemann sum defined as integral a to b f of x dx, which is limit norm p tending to 0 summation I running from 1 to n f of ti xi minus 1, which is called the Riemann integral of f. Of the function is how we define the integral connected with Riemann sum SPF. Now next, let's see the condition for existence of a definite integral. Now that we have defined the definite integral, now the question comes on what conditions does the definite integral exist. Now, condition for existence of definite integral says that integral a to b f of x dx exists if the condition is if f from closed interval ab to set of all real numbers is continuous. The continuous function, which has already been discussed in the previous sessions. The condition is this exists if this is continuous. So if the function is not continuous, then we say the definite integral a to b f of x dx does not exist. In this case, this being continuous, only then this exists. Is how we understand the condition of existence of definite integral a to b f of x dx. So let's finding integral a to b f of x dx using limit of a sum. or the Riemann sum. Is what we're going to discuss for the session. So in order to find integral a to b f of x dx for the limit of a sum, we have the formula integral a to b integral 0 to p of f of x dx. The definite integral 0 to p f of x dx is defined using the limit of a sum as limit n tending to infinity of 1 by n sigma I running from 1 to Pn of f of I by n is how we get this formula, and we just use this in finding the definite integral as the limit of a sum. So let's see some example problems through which we understand this formula more better. Now let's take an example problem where I need to find integral of 0 to 2 x squared plus 1 dx as the limit of a sum. Now this plays a vital role in understanding the method, because the question clearly says find integral of this function x squared plus 1 with limits from 0 to 2 over dx as the limit of a sum. Now since the question is exclusively on finding the integral through limit of a sum, we use the formula which we use for finding the limit of a sum. So here, as I see this integral, definite integral 0 to 2 x squared plus 1 dx, and when I compare this with the formula which you have taken in the previous case as integral 0 to p of f of x dx, then I clearly see that my p is 2 and my function f of x is x squared plus 1. So based on these two concepts, let's find definite integral using the formula for integral 0 to p f of x dx is limit n tending to infinity 1 by n sigma I running from 1 to Pn of f of I by n. So let's use this formula in order to find integral of 0 to 2 of this. Therefore, integral 0 to 2 of x squared plus 1 dx would be expanded as limit of n tending to infinity and 1 by n summation I running from 1 to Pn, p being 2, this extends from 1 to 2n, and f of I by n, which is x squared plus 1, which reduces to I by n whole square plus 1, using x squared plus 1 expanded through the function f of I by n. So this reduces as this, and this on further simplification, limit n tending to infinity 1 by n sigma I running from 1 to 2n of I squared plus n squared by n squared is what we get as the limit. Now the question comes on how we expand this summation and then use the respective formulae. Now continued from here, my integral 0 to 2 of x squared plus 1 dx reduces to the limit of the sum as limit n tending to infinity of 1 by n sigma I running from 1 to 2n of I by n whole square plus 1 is what we get here. So let's expand this directly with summations running from I1 to 2n, with each value of I substituted in the function of the summation. So in this case, I get limit n tending to infinity of 1 by n, and the summation which runs with I equal to 1 initially has first I equal to 1, which gives 1 by n whole square, and the next value of I, which is 2, gives us 2 by n whole square, 3 by n whole square, and proceeding similarly, the last value is 2n, which I get as 2n by n whole square of this. And next I have sigma I running from 1 to 2n of 1 is nothing but 2n, because it is independent of I, so I get this to be 2n. Now each of this value substituted gives me this, which on the next step is limit n tending to infinity of 1 by n, and then taking n common, because in each of the cases n is common, so I get this as n square coming out, and I have the numerators which are left inside the brackets as 1 square plus 2 square plus 3 square till 2n whole square plus 2n is how we get the summation. So each of n square in the denominator is taken as LCM out, and we get this. Now this further reduces to limit n tending to infinity of 1 by n cube of 1 square, 2 square, 3 square, 2n square of plus 2n is what we get in the next step. Now, as we know that this is clearly in the form of the sum of all squares which are integers, we have as an exclusive formula for this, which we're going to substitute in this case. So let's recap with the formula which we have identified here for 1 square plus 2 square plus 3 square till 2n square. Now, continued from here, we know that the sum of squares of integers, consecutive integers, 3 square till n square is n times n plus 1 into 2n plus 1 by 6 is what we have as the formula which we're going to substitute here. So therefore, I have this reducing to limit of n tending to infinity of 1 by n cube and 1 square, 2 square till 2n whole square is n into n plus 1 into 2n plus 1 by 6 is what we get when n is replaced with 2n on the right hand side, plus 2n is what we get. Now this, on further simplification, gives limit n tending to infinity of 2 1s, 2 3s, 1/3 of n 2n plus 1, 4n plus 1 plus 2n of 1 by n cube. Now this n cube is taken inside, but before this we have limit n tending to infinity of 1 by n cube 1/3. When n is taken common out of this, this can be written as